edges. So there's an edge between 1 and 2. It's this one. And then 2 and 3. Which one's that? That's this one. 2, 3. Okay, and 3, 4. That's this one. 3, 4. 4, 5. That's this one. 4, 5. And 5, 1. That's this one. 5, 1. Okay. Now just check 1, 2, 3, 4, 5. 5 edges. 1, 2, 3, 4, 5. Yes. Okay. So that's the complete set here of the edges. So that's one way, or it's another way of representing or describing a graph. You just give its two sets: the set of its vertices, or set nodes, same thing, and the set of its edges. Okay. Now, what's the point of graphs? Why graphs? Now, very quickly, when we just get into the first chapter, in fact, you'll see why graphs are very useful, very important for the theory of computation. Well, I won't go into it, but just accept that for the moment. Graphs are a very useful tool for computation, theory of computation. Okay, so you can these nodes here, they can represent, for example, cities, and the edges could be highways. Earlier I gave the example of these nodes here could be storage tanks. And these edges here could be pipelines, oil pipelines between storage tanks. What else could we have? I used to work in the evolution of neural networks. So these nodes here could be, and each node could be an artificial neuron, and an edge would be a connection, like an axon between two neurons. So it's the idea of graph. It's an abstraction, right? It's a generalization, and has many applications. And in computer theory, we'll have yet another use for graphs. But I won't steal the thunder. I don't know if you know that expression. Take the limelight. That will come soon enough. You'll see how to apply graph theory, the idea of nodes and edges, to the theory of computation. You'll see that fairly soon. Alright, I'll turn around. Now we talked now the idea of the labeled graph. Now here's an example of a graph where you give labels or identifiers, maybe names, maybe numbers, maybe a mix, whatever. Just some way to identify one node from another node. Now here, for example, here are cities in the US, obviously. So SF, San Francisco, Chicago, Ithaca, that's a city, I guess. In New York State, I think. And New York City, I guess. It's a bit confusing. There's a state in the US called New York, and there's a city in the United States also called New York. And to make things even more confusing, that city, New York, is in the state of New York. Right? So you get an address, blah 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 blah, New York, New York, right? Meaning the city and the state. Okay. So, and what are these numbers here? So these names here, they identify the node, right? And a node, you're using a node to represent a city, okay? And these numbers here, what are they? Well, they're labeling the edge, okay? And Now, depending on the application, the context, the modelling that you are using graphs for, you need to interpret. What are these numbers on the edges? What do they mean? Are they like distances? Are like this the number of kilometres? Or, well, it's American. America, I think, now is the only country in the whole world that does not use the metric system. It's still using miles, whereas the rest of the world uses kilometres. And they can't continue much longer. America was able. See, it's very expensive to make the switch from, say, miles to kilometres. It costs the government millions and millions. And America just thumbed its nose, gave the finger to the rest of the world in converting that, because it was by far and away the dominant economy. But little by little, America's power, relative power in economic terms, and so on, is dwindling and dwindling as Asia rises, as Europe rises. I mean, the world's biggest market now is Europe, it's not the US. So sooner or later, America will have to convert to a metric system. I mean, let's see that on the cards. So anyway, so are these distances? No. Well, in this context, they are airfares. They are amounts in dollars for a direct flight, say from Boston to San Francisco, $378. Okay, so it's an airfare. So that's an example of a labelled graph where not only the nodes are labelled, but also the links also labelled, okay? and interpreted. I mean, just labelling is not enough. I mean, I could put wiggly stick, squiggle, and mean that doesn't. It's labelling it, but doesn't mean anything. You have to interpret it. I mean, just common sense, right? You have to give an interpretation to a labelling of a graph. Okay. So city names and airfares. Okay. Okay, a new concept, a subgraph. Well, you can probably guess what it means. I've sort of drawn one example here. Now, with 6 nodes, that's the original graph, right? Call it G. And this graph here with 4 nodes, they're a subset of the original graph G. So these 4, using some, so this subgraph, well, these 4 edges, sorry, these 4 nodes here, 1, 2, 3, 4, their edges, those edges are also some of the edges of your original graph G. Okay, so these 4 edges and these 1, 2, 3, 4, these 4 nodes and these 4 edges, they are a subgraph, call it H. So the subgraph H, which is a subgraph of the bigger graph G. Okay. So I've drawn it so that your subgraph H, the nodes are drawn with filled in, heavy filled nodes, and the edges of your subgraph are drawn with a heavy line, and the other edges not a member of the subgraph H are drawn with dotted lines. Okay, so this thing here, so with these 4 edges and 1, 2, 3, 4, sorry, God, I keep saying that. These 4 nodes and these 4 edges together, that's a subgraph. That would be your subgraph H, right? And the whole thing is your graph G. Okay, so the notion of a subgraph. Right. Well, we'll just for the next session, just more definitions. And how many more? 1, 2, 3, 4, 5, 6, 7. Well, nearly a dozen. Or maybe 10 or something. Okay, so till next session.